We're going to decide what type of function do we want to use. And remember, we're setting these parameters. So you can try lots of different things, but you cannot ask the magic oracle what's the best function to try. Try all the ones you want. For instance, you could try a linear function, you could try a polynomial function, you could try a decision tree, whatever you want to do, but you decide what type of function you want to use. And then the third thing you need to know is what is the loss function. So I have two functions in the picture. I have the function I'm actually going to be fitting, which I might call the prediction function. I have another function called the loss function. All we are doing, function, we're typically going to have parameters, and parameters are numbers that are going to change. The goal of any machine learning algorithm is to find the parameters of the prediction function that minimize the loss function on a given set of. So I made up the data set so we could practice this. So my data set has two variables, and I'm going to say x is the feature, and there's only one feature, and y is the target. 1, 1, 2, 4, and 3, 3 is my data. And I am going to try to fit, what type of function do you want to use here? Yeah, we're going to use linear. We're going to use a linear function. So our function is going to be of the form f of x equals a0 plus a1x. For right now, since this is new to us, let's do mx plus b. But when you're doing this for real, it's going to be a0 plus a1x. Function is going to take these parameters m and b, which are standing for the function. Here are my parameters. There are two numbers that I can adjust here to make this be. I'm going to take the error, which will be the difference between the prediction minus the actual value. This is the prediction for y minus the actual y. I'm going to square it, and I'm going to sum them. And these are the three pieces of my problem that I'm going to be looking at. We can think of the loss function as taking in m and b, since those are the two parameters. If I take in m and b, I'm going to make three predictions. I'm going to have m times 1 plus b as the prediction at x equals 1. Whatever m and b are, this prediction will be m times 1 plus b. And the prediction at x equals 2 will be m times 2 plus b. And the prediction at x equals 3 will be n times 3 plus b. I want to take the error for each of these terms, which will be the difference between the y and the prediction. So the error for this term would be m times 1 plus b minus 1. I have m times 2 plus b minus 2. I have m times 3 plus b minus 3. And then my error squared will be m times 1 plus b minus 1 squared. And then m times 2 plus b minus 2 squared, and then m times, wait, that's 4, right? Don't let me say nonsense. This is 4. Now the sum of the squared errors as a function of m and b will take m and b as inputs, and it will return these three things added together. M plus b minus 1 squared plus m times 2 plus b minus 4 squared plus m times 3 plus b minus 3 squared. This should be a 3, right? That's why we have computer. So here's my layout. Final loss function will be this. Tell me the linear function f of x equals mx plus b that you want to use. This tells me how good it is. The lower this value is as a function of m and b, the better the fit is. So let's see what this actually looks like. So I have my data here, x and y, which I said was 1, 1, 2, 4, and 3, 3. And then I can make y equals mx plus b, and I can just treat those as sliders. And like, that's a really good fit. I don't know if I can get a better one, but maybe I can. So now let's look at what the error should be. We wrote down the error formula here, and I'm just going to reproduce it because I can do that calculation. So I said m plus b minus 1 squared plus m times 2 plus b minus 4 squared plus m times 3 plus b minus 3 squared. This is my error that I just wrote out here. This is the sum squared error term. See, I even made an error when I was typing it, so you'll be able to remember that. So right now my sum of squared error term is 3. The error went from being 3 to being 8.5. Okay, so let's make b be negative 0.5. Nope, that increased it. Okay, so negative 0.5 and then increase the slope to what? I'm going to tell you, I think you're taking way too big a step. I mean, we could play this game all day. It was 3 when we started, so I want y'all to try this. See if you can come up with a better number than 3. Do not take these huge leaps of faith. Like, progress, friends. You said, I think the 0.999. We got 2.99 down here. That's 0.9 is 2.74. That's way down from 0.8. Was that better or worse? I'm going to stick with 0.9x plus 1 and see what can I do with the b. That's lower. We're trying to find the m and b values that make this error function as small as possible. So right now the number to beat is 2.68, and you said 1 for m and negative 1/3. So m plus b minus 1 squared plus m times 2 plus b minus 4 squared plus m times 3 plus b minus 3 squared, or m and b. Let's see if we can do anything with that. Okay, it says, I think you were really close because it says that the minimum value occurs at and m equals 1, and that gives us 2.67. And then if we say, take that, we get slightly better at 2 2/3. And Wolfram Alpha told us that that was the smallest we could make it. So I think maybe visually, maybe, I don't know if you have this intuition yet or not, but if I have this value that b is 0.66667 and this, do you see how if I bump this just a little bit, it looks like the fit gets a little bit worse. Maybe it's too subtle, but you can see the number getting worse as I move away from these values. So what we did there was we set up the data, we set up our type of function that we wanted to do. We looked at the parameters of that function, developed the loss function to tell us what made this be good. And you can see why the loss function works here, because what this loss function is measuring is the difference between the predicted value and the actual value. And the reason we're squaring it is we do not want it to be able to play tricky games where it can overpredict some and underpredict others and then get good cancellation to trick us. So by squaring, we make all of the errors count positively. And if these predictions are close to the actual values, this should be small. If the predictions are way off, you'll be squaring big numbers that will then become big numbers and you'll have a large error. So that's why we want to minimize this loss function.